Do we have any questions on acids and bases? pH? Should we start? What? Should we start with an example of kind of review what we learned last time? Maybe?
Yeah.
Okay.
Because it's still on both sides we have hydrogen and we say the same thing.
Okay. So let's start with the simple acid-base reaction. Let's do. Let's just do this. Oh, thank you. All right, let's start with this simple acid-base reaction. Can anybody predict what might form? That's right. What's going to form? Well, who's going to donate the hydrogen ion? Who's going to take it?
When gives oxygen starts reaction.
So what'd you say, Chad? Yeah, here's our acid. Can we all see that this is our acid?
It's a strong acid, isn't
It is a strong acid. Yes. How come that's not an acid?
Because of oxygen already told the ion.
Because that's the acid. Right? That's why. Because water could be both an acid or a base. It's amphoteric, right? Remember that? So since this is and this cannot be a base, therefore this has to be the base. You following?
Why does the second one the base?
Why does water have to be the base?
Always water is the
No. Sometimes water could be the acid. It's the base here because this has to be the acid. Because that's not a base.
base. Always this the base is on second.
No. Nope. I could rewrite this to be H2O plus H2SO4. It doesn't matter how you add it, right? A plus B is the same as B plus A. Doesn't change. Okay, thanks for asking. So this one donates an H plus or 2, right? And I'm never going to have you predict one like this. For example, the answer could be H. So if it donates 1, it's HSO4 minus, right? And what does H2O turn into? Hydronium, H3O plus. Good? All right, so if this is the acid, this is the base, what's the conjugate acid? Hydronium. How do we remember that? How do we know? Because the base turns into an acid. Yeah, it gained it accepted that hydrogen ion, and now it's an acid, right? And the conjugate base would be, is this a base? What tells us it's a base? Because it has a negative. It donated one, and now it has a negative charge. So now that it can take one, if possible, right? Any questions on that? Yeah.
Explain again why when H2SO4 donates a hydrogen, why it loses a charge, why it gains an electron. Oh, well, because
Are we good then? Because it's an H
I guess
plus,
so.
it loses an H plus, it loses a
So,
positive charge.
Right,
That means it has to be negative, because it was neutral.
right.
Good?
That's why H3O plus.
Gain the plus, that's why it's plus, because it
Lost
gained the
one.
H plus. It didn't lose electrons necessarily, it gained an H plus.
Okay.
It gained it was neutral, and now it gained a positive charge, and so it's positively charged.
Gotcha.
Good? Anything else? Yeah.
Sorry, I'm still trying to wrap my head around it. Is H, like, why is H plus again? Because it doesn't have a proton and an electron.
Because, what's the definition of a base?
A proton acceptor.
A proton acceptor. So, once you determine which one is the acid, which one is the base, the acid gives up a proton, or a hydrogen or an ion, and the base takes in or accepts the hydrogen ion.
Well, I guess why is it an ion? Because we're,
Why is hydrogen an ion? That's what makes it an acid. Right? This is aqueous solution,
okay.
and this is liquid water. This is aqueous, and this is aqueous. So do you remember what happens in an aqueous solution? You throw a salt in there, and then what happens? It dissociates. Okay? So this will dissociate into two H pluses and a SO4 2 minus. Right? This doesn't dissociate because it's a covalent compound. But what happens is it takes one of those guys and makes this. Good? All right. Any questions on acid-base reactions, conjugate acids, conjugate bases? Okay. Last time we talked about pH. So let's do a problem where we have to deal with pH. Okay. What is the pH of a 0.0105 molar concentration of magnesium hydroxide solution? So how do we go about doing this? You can look at the mole roadmap, and I'm not confident that you'll be given that mole roadmap on the exam. I mean, you'll be given the small one, but I don't know about the whole thing, right? So let's say worst case scenario, we don't have that to look at. So what do we do?
Be sold the problem.
Put it on your note card, okay. Sure. Okay. Oh, something bad happens, like, oh, I forgot last minute. Okay. We're just worst case scenario. Well, we use what we do know. What is on the equation, right? It says pH is equal to what? And this is what we're looking for, so we have to know how to calculate it, right? Negative log of H plus concentration. Okay? Ooh. Does this have any H plus concentration in it? No? Okay. Well, it has OH. Okay, so what can we find? What, using the equations on the reference sheet? What? POH. What, sorry.
I thought it was a base.
Yeah, this is a base, so there's no H plus ions in there. So we can find the POH. Since we're dealing with an OH or a strong base here, we're going to start with the POH. You with me? And POH is equal to negative log of hydroxide ion concentration. And these are all on our reference sheet. You following? Okay, do I know my hydroxide ion concentration? Can I find it? Where do I start? With what we know, right? Start with what you know. This is what we know. So we can start with 0.0105. How should I write that? Moles of magnesium hydroxide per 1 liter of solution. Y'all with me? Okay. All right, now what? We still want concentration, so do I need to get rid of this liters? No, we need to keep it, because we still need moles per liter, right? So we just need to change this into what? Moles of OH. That's it. So if we have 1 mole of magnesium hydroxide, how many moles of OH do we have? 2, right there. Y'all with me? 2 moles of OH minus. That cancels. Now we have concentration of OH minus. Woo! And now we can plug this into this formula. Does that make sense? So let's find this. 0.0105 multiplied 2, that's 0.021 molar concentration of OH minus. You following so far? Okay. Then we take the POH is going to equal negative log of that concentration, 0.021 molar. Okay. And we get that the POH is 1.68. Is that our answer? No, we need to go back and need to make sure we know what we're looking for. We're looking for pH. How do you find pH if you know POH? There's another formula. 14 minus the POH is equal to the pH. Good? You don't have to memorize that. It's on your reference sheet. You just have to know how to use it. So 14 minus 1.68, and that's going to give us 12.32. That's my pH. Do you see how you can step your way through it without the mole roadmap? Now, should we use the mole roadmap? Okay. Okay. So we are looking for the pH. And what do we know? We know the concentration of our base. From there, we find the concentration of our OH minus. Then we do negative log of OH minus to find the POH, and then 14 minus the POH to find the pH. That's what we did. So if you guys, definitely put it on your little card, and if you don't have it on your card, you could still do it, right? We good? Any questions on pH and POH so far? Good, ready to move on? All right, let's do the inverse calculation. And this is also on a reference sheet, so no big deal. Now let's say we have the pH, but we want to know what the concentration of our acid or our base is. I'm not going to show you the logarithmic algebra unless you want me to. I'll just give you the formulas because that's really all you need. Anybody want me to show you the math? Yeah? Okay, yeah, I'll show you. pH equals negative log of our H plus concentration. Good? Now we can do a little bit of algebra. Divide by -1 to both sides. That makes that negative. You following? So we have negative pH is equal to log of the H plus concentration. Now what's the base of our log? Does anybody know? It's 10. It's log base 10. We don't have to worry about that because on our calculator it is log base 10, right? So the inverse of log, to get rid of the log, just like any other algebraic operation, we do the inverse operation. If it says add, we subtract. If it says multiply, we divide. If it says square, we square root, and so on, right? The inverse operation of log is 10 raised to that power. So if we do this to both sides, we get that the hydrogen ion concentration is equal to 10 raised to the negative pH power. This is all you need. And I could do the exact same thing with POH, and I'd get the hydroxide ion concentration is equal to 10 to the negative POH. Good? So if you didn't like that math, don't worry about it. You don't have to do it. But that's how we get that. So now we can calculate the concentration if we have the pH or the POH. Or if we have the pH of a base, we can convert it to POH of the, right? And then find the OH concentration and convert it to the concentration of our base. Did you follow what I said? Okay. So let's go back to here. If we're looking for this, and we know this, we just go the other way. We find the POH, 14 minus the pH. Then we do 10 to the negative POH, and that gives us our concentration of our hydroxide. And then we convert it, depending on what the ratio is of our hydroxide to our base. So just the opposite. Does that make sense to everybody? And if you have this chart, it makes it pretty straightforward. But you can still do it without it if you don't have it. I'm not saying you shouldn't write it. I'm just saying. Okay? Should we do some examples? Okay. So first example, I'll write it out because I know that makes it easier for you. It's like, okay, help us to know how to do these problems. How many moles of HCl are contained in 850 milliliters of a solution with a pH of 3.2. How many moles of HCl are contained in 850 milliliters of a solution with a pH of 3.2? Should we use the map to guide us where we're starting, where we're going? Okay, what are we looking for?
Moles of H2O.
Moles of HCl. So where is that on our mole roadmap?
Moles of
It's an acid, right? So we're going to do moles of our acid. That's what we're looking for. Does that make sense to everybody? And if we're looking for the base, we'll do moles of the base, B. Okay? All right. So what do we know?
volume of the
We know the pH. The volume's gonna be right here, so we're gonna use it in that step, right? So the furthest part away is the pH, so that's where we start. Good? And what are we gonna do? We wanna go this way, so we're gonna do 10 to the negative pH. And that gives us our H plus concentration. And what's the ratio of H plus to, in this case, HCl? 1-to-1 ratio. So basically, whatever it is for here, that's what it is for the acid in this example. You with me? Because that is a 1-to-1 ratio. And then we're going to multiply our concentration by our volume. But what do we have to do? Change it into liters. Because this is molarity, moles over liters. If we multiply by molarity, does any unit cancel? No. Always use dimensional analysis in chemistry. Always. Can help you to know if you're doing it right. Because I know sometimes chemistry feels like a whole nother language, right? So, there we go. That's our plan of action. Now let's do it. So we're going to do 10 to the negative 3.2, and that's going to give us our H plus concentration, or it's also our concentration of HCl, right? Because it's a 1-to-1 ratio. Can you all see that? Should I do it like we can't see that? Let's do. So we do 10 to the negative 3.2, and we get 0.00063 molar concentration of H plus. And so I have my concentration of my, 3 zeros after the decimal. And that's moles of H plus to 1 liter of solution. Good?
So where are you getting the 6.3 from the 3.2?
10 raised to the, did I do it wrong? 10 raised to the negative 3.2 power. That gives us,
You're right.
that gives us this value.
Yeah.
Thanks for stopping. Make sure we get it along the way. Otherwise, I'm just dumping the stuff and it's not helping. Yeah, always ask. Thanks. Okay, so we want to know moles of HCl, so we better change this to moles of HCl, right? And what is the ratio of moles of HCl to H plus? It's a 1-to-1 ratio. Can we all see that? It's a 1-to-1 ratio, okay? So 1 mole of H plus to 1 mole of HCl. And if we could see that, do we have to worry about this step? No, as long as you can see that. I mean, if that doesn't make sense, you say, well, why can we just do this? No big deal.
Why is it 1-to-1 again, sorry?
Because if we have HCl, it breaks down into H plus and Cl minus.
So if it was like 2 for.
But if it was H2SO4, is that a 1-to-1 ratio? No, there's 2 hydrogens for every 1 sulfate. Yeah. So you don't even have to write the equation like I did. Just look at it right there. Does that make sense to everybody? Okay. So then moles of HCl go away. Now I have moles per liter of my HCl. I don't want moles per liter, I want moles, so I better use this guy. Okay, 150 milliliters. But does it cancel? No, it doesn't, so we got to convert that into liters.
Is it more, in liters? 850?
Milliliters. So that goes away, and now the liters goes away. And that's it. Our answer is left with moles per liter, moles of HCl. Tells us we're done. Multiply, divide, and we'll get 5.36 times 10 to the negative 4 moles of HCl. If I did my math right. How are we feeling? So it's quite a bit of dimensional analysis, especially if we were going from, let's say we didn't have a balanced equation. Now, if we have a balanced equation, the easiest thing to do is just to use the mole-to-mole ratio, right? But essentially, we can go from moles of our base all the way to moles of our acid this way. Now, that's a long way, but we could, right? Definitely, if you have a balanced equation, use it. It's way easier, right? Good? How are we feeling? All right, let's put it all together then. Did you guys do your titration lab yet? You did?
Yes.
Oh, so I'm a little bit late showing you. Did we understand it? Okay, let's go through it, and show you kind of what we're doing. So, in your lab setup, you have your burette, right? And you have your little stopper there, and you have your Erlenmeyer flask or something like this, and you have it on a stir, right? Is that right?
Yes.
Okay, so this is your stir. And here you have a known volume and known concentration. No, you don't know the concentration, right? You know the volume of the acid. I'm just going to say HCl to keep it simple, right? Maybe in your lab you used citric acid, right? I don't know. I don't know what you did. Okay? So we're looking for the concentration of my HCl. We know this. Let's say this is 3.5 liters. That's a whole lot of it. Well, let's just say, okay? And then in the burette, and it's not floating in midair, right? Okay, I'm just teasing. Okay, so we have our sodium hydroxide in here, and we know its concentration. Its concentration is, well, I don't, I'll just do this. Yeah, that's okay. 2.40 times 10 to the negative 2 molar concentration of NaOH. Now we got to know how much we put in, right? Because if we don't know how much we put in, how much neutralizes, and if it neutralizes, we're going to have NaOH neutralizes with HCl, and what do we get? NaCl and water. Just a double replacement reaction. And it's balanced, so we're good. All right, so now we're going to drip this in. We have a phenolphthalein indicator in here, right? Is that what you used? Okay. And you drop it in here until it just barely turns pink, right? When it barely turns pink, that's when we reach the equivalence point where it's neutralized. And then if you did it perfect, and the big question is if, right? Then you can drink it and it tastes like what? Salt water. That's all it is, right? Don't do this. Never do this. This is how often are we perfect? Never, right? So, but in theory, we could drink it, it would just be salt water. So we drip it in there, and once we drip it in there, we can measure how much of it that we use. And let's say we used 58 milliliters. We can now calculate the concentration here, but let's say we don't just want the concentration, we want to know the pH. Good? So once we know all of this, this is where we use the math, right? This is where we use the dimensional analysis. This is where we use our mole roadmap to convert it to what we're looking for. In theory, this is what it should be. You with me? You understand why we do this stuff? Now we can determine what the concentration of our acid is or what the pH is. The easiest way would just be sticking your stick in there, right? Oh, that's the pH. Okay. but we can determine the concentration the same. Good? All right, so that's titration. And it's used for neutralization reactions only, because if you have a weak acid and a weak base, is it going to neutralize? Not the same way. Okay? So let's pull out our chart, our map. So here we know this, right? We know everything about our base. Should I go this way to find the pH? No, because we have a volume. We have to go this way, right? So we have to multiply our concentration by our volume, and we have those two, and that gives us this. We look at our balanced equation that we wrote, the 1-to-1 ratio, we get that. Then we divide by the volume. We did have the volume, make sure it's in liters in both cases, and we get the concentration of our acid. And really in the lab, that's all we're looking for, right? And then if we wanted to calculate the pH, we could. Does that make sense to everybody? So we're not going to go this way because there's a few other known values we have to use. Should we do it? Woo-hoo. Okay. All right, so what am I going to start with? I know everything about that guy and a little bit about this guy, and this is what I'm looking for. So I'm going to start here. Good? So 2.40 times 10 to the negative 2 moles of NaOH to 0.5, well, sorry, I should say 1 liter of solution. And then I'm going to multiply by the volume and make sure that's in liters so that it cancels. Does anybody know how many liters that is without doing the math? Yet? Can we do that yet? It's always divide by 1,000, right? So 0.058 liters? No. 0.058 liters. Okay. So that goes away. And does that confuse anybody? Should I convert it? I can. If it makes you feel a little warm inside, we can. Write it out and everything cancels. Okay. Now we have that. We can use the mole-to-mole ratio from NaOH to HCl. What's the ratio in our balanced equation? 1-to-1, so 1 mole of NaOH to 1 mole of HCl. That goes away. And now that we have our moles of HCl, we have our volume. So what do we do with it? Divide. And if you forget, it says right here what we do. Yeah, we divide because we're going this way, right? But dimensional analysis will tell us what to do. We want molarity, so liters has to be on bottom. So what is it, 3.5? So now we have molarity of HCl, and we can find the concentration right there, be done. Well, we're looking for the pH, so what do? Convert it to H plus. Oh, what's the mole-to-mole ratio to H plus to HCl? It's a 1-to-1 ratio. So really we're done, right? So our H plus and our HCl is going to have a concentration of 3.98 times 10 to the negative 4 molar concentration of H plus. Then from there, we do pH is equal to negative log of that concentration. And we get 3.4. Good? Questions? Did I do my math wrong? What question do we have?
Where do you get the concentration for the H?
Right here?
Yeah, like
Okay. So from here we have moles over liter of HCl. Okay? What's the mole-to-mole ratio of H to HCl? It's a 1-to-1 ratio. So we have a 1 here and a 1 here. Does that change anything? It doesn't. So this is the concentration of my HCl, but it's also the concentration of my H plus. Make sense? Thanks for asking. And then I throw that in my formula to get my pH.
So wouldn't the concentration of H plus be half of the total concentration, because it's only half of the cake?
No. Why? Because the ratio is 1 H plus to 1 HCl.
Right.
Maybe I'm not understanding your question.
No, I'm not understanding this concept. So I have like a liter of water, right?
Uh-huh.
And I have
A liter of add.
1 mole of HCl. Wouldn't I have half a mole of H and half a mole of Cl to make?
Mm-mm.
Because I would have 1 whole mole of H and 1 whole mole of Cl.
So if we had 1 mole of HCl,
Yeah.
we have 1 mole of H and 1 mole of Cl.
So
So
it's going to be the same
yes,
concentration. But if it was H2Cl, then there would be.
then it'd be a 2-to-1 ratio.
Yeah.
Yep.
Okay. So
Yes.
then you would have a different concentration.
Yep.
Okay, I get it.
Does that make sense to everybody? Thanks for asking.
Yeah.
Good? No?
I'm on the same page as him. I hate moles, like 1 plus 1 equals 1.
Yeah,
I don't get how that works.
Let me think of a way to help
CL
that.
equals 1 mole. I just have a hard time wrapping my head around it.
1 mole. This is like.
So
when we first learned
remember
moles.
what moles are. What's a mole? 6.022 times 10 to the 23 particles of that substance. Well, in that substance, if we have 6.022 times 10 to the 23 HCl particles, how many of those do we have?
That many.
That many of them,
Yeah.
right? Because this makes up 2 different particles.
Yep. This is
So
like,
if we want to know how many atoms, how many ions we have 2 ions for 1 HCl.
right.
That means we're going to have 12.044 times 10 to the 23 ions. You with me? But we're not interested in ions.
Right.
We're interested in moles. If we have 1 mole of this, we're still going to have 1 mole of that and 1 mole of that. and it's because of that number. But we don't ever want to have to use that number again, do we?
No.
No. You might have be asked that on the final exam one more time, but yeah, that's why we can do that as a mole-to-mole ratio. Because 1 mole of anything means 6.022 times 10 to the 23 of that thing. Doesn't matter what substance it is. Good?
Yeah, that makes sense.
That clear things up, Andrew?
More or less.
A little bit? Okay. All right. Any questions before we try tackling the last topic of acids and bases? Questions? No? All right. Excuse me. I have a drinking problem. Don't worry about it. All right. Let's talk about buffers next. And you may have learned about buffers in biology, right? What are buffers? What are buffers? Anybody know? It was one of those really hard things. They just said, I don't know. A lot of terminology in biology. Sometimes it probably just goes over us, maybe, right? Okay. Anybody know what a buffer is? Yeah, we use a buffer solution so that we can change the pH of a solution, or in the case of our bodies, we can change the pH of our bodies by adding a strong acid or strong base, and it changes it just a little bit. We don't want to go from alkaline to very acidic, or very acidic to way too much basic, right? We kind of want to be somewhere neutral. So we add a strong acid or strong base to a buffer solution, which is our body, and it'll change the pH slightly. And we can do it however slight we need, but it won't just way too much. It's like, okay, now it's overboard the other way. Now I got to go back, and you're just going back and forth, back and forth. So we just use that buffer solution to just make incremental changes. Does that make sense? So these are used to maintain a stable pH or a desired pH. So a buffer consists of a weak acid and a weak base. So we kind of talked about this a little bit. How do you tell how do you tell if it's a weak acid or a strong acid, a weak base or a strong base? Do you remember? What?
The table, the numbers.
What? No, like the pH numbers? Okay, sure. Yeah, that's one way. But by definition, a strong acid, dissociates completely. What does that mean? It dissolves all the way. It's 100% soluble in water. Do we know what substances are soluble in water and what substances are not? Remember that chart that we learned back in precipitation reactions? Okay. So if we have a substance that is always soluble, if we throw it in water, it's going to completely dissociate. Now, we might not call it a strong acid, If we take, for example, sodium chloride and put it in water, well, we don't call that a strong acid, but it's completely soluble, right? It completely dissociates. So what do we call that? A strong electrolyte. Remember learning that? It completely dissociates. An electrolyte is where you have your ions in your solution. You have these charged ions in the solution. It makes it conductive to electricity. Okay? So that's a strong electrolyte. The same way, a strong acid is a strong acid the same way. It completely dissociates. So what's a weak acid? It's still an acid, so it's still aqueous solution. It's still soluble, but it's only slightly soluble. Slightly dissociates or partially dissociates. So those insoluble compounds on our solubility chart, a lot of them are slightly soluble. When we talk about ionic compounds, they're not just insoluble, some of them are, but most of them are slightly soluble. Are we good? What about a strong base and a weak base? Same thing, right? Strong base is where it completely dissociates in water. Weak base is it slightly dissociates in water. Yeah, well, water's the solvent, the universal solvent. If we put HCl in milk, well, is there water in milk? Probably. And that's the part that makes it acidic, right? You have to have, so HCl as a gas, that's a covalent compound, right? But if you throw it in water, it dissociates like an ionic compound does. So, does that make sense? All right, so strong acids that you need to know. Do you remember what these are yet? So somebody tell me. HCl. H what? Oh, is that what you said? HClO4? Yeah, sorry. HClO4, HCl, H2SO4, HI, HBr, 1, 2, 3, and HNO3. Why are those strong acids? Because they're with soluble ions. They completely dissociate. There are some exceptions to that. But the thing is, we don't have to worry about it. If we know what our strong acids are, do we know our weak acids? Yeah, it's everything else. Okay? So if we know that, that's going to help us in this section. Okay? What about strong bases? What are the strong bases? Basically, anything with OH minus, right? Now, there are exceptions to that, right? Because OH is OH on our solubility chart? That means OH is normally an insoluble compound, but when is it soluble? When it has soluble ions in it, like group 1 ions. Some group 2 ions are exceptions to OH minus. We didn't talk about the exceptions to OH minus. So for this class, we're going to keep it simple. We're going to say, if it has an OH in it, it's a strong base. Fair enough? Okay. There's a little bit more to it than that, but we're not going to worry about it here. Good? And examples of weak bases that we need to know, or one of them that's not. So weak bases are anything with a negative charge on it that can accept a proton, right? So one weak base that we need to know that doesn't really follow that pattern is NH3, right? We talked about that, ammonia. Because if it accepts a proton, it becomes ammonium ion.
That's bleach, right?
What?
And that's bleach, right?
Nope, bleach is, what is it?
Don't worry, we can move on.
Okay, I don't remember the formula for it, but it's sodium, I can't even remember the name of it.
I'll look it up.
Okay. All right. So to get into the technicality of it, it's the strong acid in equilibrium has an equilibrium value much greater than 1. Much greater than 1 means it highly soluble. It dissociates completely. And a weak acid, then the K is much less than 1.
Why are there double alligators?
Because it means much less, much greater, like, right?
Sorry, can I just make a comment?
Yep.
I feel like in this class, I've seen more different kinds of like equal signs and more than the rest of them I've ever seen. Like I've never seen like the squiggly one.
Like in a
I've never
math
seen,
class,
like,
right? You've seen,
I just-
we do more math in this class than you do in a math class. Is that what you're saying?
Dude,
Yeah.
literally, yeah.
It's like-
And that makes me feel so good. Do you want to know why? Because
using it.
that's why we learn math, guys. It really is. We don't learn math to just do all these cool puzzles and stuff.
Yeah.
Really. We do math for science. Why do we do science? For engineering and the trades. That's really why we do it, for applied science, right? Science is applied math. So, anyway, you just struck a nerve and made, oh, okay. A good nerve, okay.
Nice to actually use it.
But yeah, I remember teaching physics at high school a long time ago, and a student gave me a letter. He says, I learned more math in your physics class than I learned in my math class. I'm like, heck yeah. That's because that's where it's useful. And a lot of times people in math, you learn in math, like, I'm not ever going to use this crap. Right? You ever feel that way?
All the time.
It's because it doesn't mean anything until you actually use it for something real. Okay, but anyway, that's why I went. Did I tell you guys I wanted to be a math teacher for my whole life? I did.
You woke up one day and you're like, I'm gonna be a math
No,
teacher?
ever since 4th grade, I remember. I loved math in 4th grade, and I loved it ever since. And I thought, okay, I'm gonna be a math teacher. I mean, what else can you do with math besides teach it, right? And so then I took a physics for engineers. Like, oh yeah, this is where you use math. And so I decided, okay, I'm gonna teach physics. So I taught physics, and lo and behold, now I'm teaching chemistry. But anyway, sorry. I'm okay. Okay. Yes, what a nerd. Okay.
I mean, that started, when you became a professor, teacher, whatever.
Uh-huh.
Yeah, you're all super nerds.
Yep. All right, we're all nerds in some way or another, right? At something, but maybe not at math or science. But okay. Sorry about that tangent. Anybody have a question or comment before we move on?
So double alligators just mean very much more than one or very much less than one?
Yeah.
Okay.
So an example, this would be like 2,000, right? Remember we said that the equilibrium constant K is going to be between 1 and, right? And if it's much less, an example would be 3.2 times 10 to the negative 6. Very small, right? Very much less. Not negative, but very much less than 1. Good?
But it'll never be a negative, right?
Yeah. Or, yes, that's right. Okay. All right, so do you guys remember the equilibrium constant equation? Where it said K is equal to C, D, D over A, and B. Do you remember this at all? Do you remember how we come up with this formula? From our A plus B gives us a C plus a D, right? The products over the reactants, okay? That's the same way, but now when we have an acid-base reaction, then we're going to have some acid. We know this is an acid because it has an H plus, right? So that's an aqueous form, and it's in equilibrium with an H plus, also an aqueous form, plus the A minus. This is our conjugate, or our conjugate base, right? And that's also aqueous form. So in this is our general equation for an acid-base reaction. What happens to the acid anyway? Good? So from here we could say that Ka, why do we say A? For the acid. The Ka, and we're going to have this equilibrium situation for weak acids and weak bases. Okay? But we're not interested in the Kb. We're not interested in the base so much, but just the acid. That's why we broke it up and we only deal with the acid. Does that make sense, kind of ish? Okay? So Ka is equal to what?
H plus times A
Good.
minus over HA.
That's it.
Actually, I'm reading
And you're just reading off your reference sheet, right?
it. Yeah.
Is that what you get on your reference sheet, or do you get this one on your reference sheet?
Yeah, I'm
Equals
looking at the,
Ka times Ha all over A minus, is that right? This is the one we get on our reference sheet. So if we have the Ka value, and we have the concentration of our acid and the conjugation of the concentration of our conjugate base, then we can find the H plus concentration, which will then give us our pH, right? Are we okay with that? It looks a little bit like, I say Chinese because Chinese to me is like, whoa, how did they even do that, right? But it's really a new language, kind of, right? All right, should we do an example? Yeah.
What does HA?
So good. HA, this is my acid, or I should say weak acid.
Why is it weak?
Why is it weak? Because when we use equilibrium, we're dealing with weak acids and weak bases. If it goes neutralizes completely, it doesn't go back,
Oh,
right?
right. I did it. Nice try.
Yeah, because when you have a weak acid, weak base, then our weak acid turns into a conjugate base, right? And our weak base turns into conjugate acid. We still have an acid and base over here, so it can go the other way and just keep going back and forth. Does that make sense? So when it's in equilibrium, we're going to have our Ka value. And generally, you'll be given that Ka value. Could we?
What is it equilibrium?
It won't always be in equilibrium, but it can be. Once it is in equilibrium, it'll have some equilibrium constant. Good? All right, should we do an example using this? That's where we really care, right? We don't care about how math is involved with science. We just want to do. Okay. So let's do an example. Okay, a buffer solution is made from .060 moles of HCOOH, and it turns out this is the H that makes it acid. So hold on, it's written on the wrong side. Does that matter? No, it's just, this is just the structure of this compound, and that's why it's.
Sorry, know that because anything with an OH is going to be strong base.
No, this is called formic acid,
H2CO2.
and the polyatomic ion is this. And so the H plus comes in to this side.
Okay.
No big deal. I probably shouldn't have said anything. You'll be fine, just, anyway. Okay, so it's made of that number of moles of formic acid and 0.050 moles of its conjugate base. What's its conjugate base? HCOO minus. In 1 liter of water. We want to know what the pH is. You have to also be given the Ka value, which is 1.8 times 10 to the negative 4. What's your question?
Is it 0.050 milliliter of H?
Of moles of HCOO minus,
Oh,
which is the conjugate, which is the conjugate base of our acid. Yeah, Chad.
So we know it's a weak acid because the constant is.
Because it's not one of our strong acids.
Yeah, it's very much lower than 1.
Yeah, but sure, yes, but it's also not one of our strong acids, and that would be the easiest way to tell.
But also you have to give us the Ka.
Yes. Yep.
So that's another.
You'll have to be
obvious
given
tell.
that. Otherwise, then you're gonna have to do a whole lot of science that we've already done the science. We have all these Ka values. Why not just use them, right? Yeah.
Why there is 0.06 mole of H and then 0.050? Isn't that the same, like, formula?
Good question. Should it be because it's a 1-to-1 ratio?
Yeah, it's the same thing basically. Like HCCOOH and CCC.
Yeah. Maybe we lost some. I don't know. But let's just keep it simple. It is that's what we have, and maybe this is a poor example of real life. I don't know. Okay, we'll just go with the example. It's kind of like, sorry. Okay. So if we want to find the pH, what do we have to know? Well, there's an equation that says pH equals negative log of H plus. That's on our formula, on our equation, on our sheet, right? So we got to know our H plus concentration. Okay. So there's another formula that we just learned. Equals Ka times our HA all over our A minus. So this is our conjugate base. and this is our weak acid. Right? So we just plug all that stuff in our formula, and our Ka is 1.8 times 10 to the negative 4 times our HA concentration. Do we know our HA concentration? This is my HA, right? And this is my A minus. Okay. What's my concentration? We have 1 liter of this stuff.
So it's just.
So it's the same as the moles, right? Okay. So it's going to be 0.060 moles per 1 liter, which is still 0.060, right? And that's concentration there over concentration of my conjugate base, 0.050. And what cancels? Molarity. Well, actually, it doesn't really cancel, because that's what we're going to get, right? All right. So now we do the math. Does that make sense how we plug that in? We do the math and we get our H plus concentration is equal to 2.1 times 10 to the negative 4 molar concentration. And then from there, we can plug it in our pH equation, negative log of the H plus concentration. We have the pH. And that's going to give us 3.67. How are we feeling? Okay, we just got a little bit left. Let's see if we can finish by break time. Okay, let's do another example. Maybe we shouldn't finish because I got to take a break. You guys want to take a break early?
Sure.
All right, let's take a break. 10 minutes. Get started again. We just did one example, right? Yeah, let's do another example. Okay, this time, let's add. So if we add 0.013 moles of a strong base, sodium hydroxide, in 1 liter of solution of 0.06 molar concentration of our HCOOH. So this is a continuation from the last problem. So we also have 0.05, that's should be moles of my HCOO minus. And my Ka, it's a constant, so for this particular acid, my Ka in equilibrium is still 1.8 times 10 to the negative 4. So now I want to know what it does to my pH if I add this. What?
HCOH or HCO?
Well, I got 2 of them. One's my weak acid, and one's my conjugate base. Okay. All right, so, and I'm going to kind of just show you how we go through this, how we change the pH just slightly. it's not too complex, but sometimes the algebra can really be, okay? And for the, I won't ever give you anything that is too much algebra, okay? But just to show you kind of how it's used, more than anything else. So we have our 0.013 moles of our strong base added. So that means, let's see.
Sorry, are we looking for pH?
Yeah, I'm looking for the pH after we add our base. Okay, so when we add a base to an acid, it takes away from our acid, making it more basic, right? Does that make sense in your mind? So what are we doing to the conjugate base? It's kind of like we're adding more base, right? So when we add a strong acid or a strong base to a buffer solution, then we use the same formula. H plus is equal to Ka HA all over A minus. Okay, we use this same formula. Now let me show you how we implement this. So this is my acid. And so we're going to have my Ka value 1.8 times 10 to the negative 4 multiplied by my, since I'm lowering my my acid, I start with, since it's all in 1 liter, and let me tell you, what if we did in 3 liters? Would that change our numbers? It wouldn't, and here's why. I'm going to just show you this on a side note real quick. So this is my concentration. If we have 0.06 over 3 liters, right? And over here, we have 0.05 over 3 liters. Well, it cancels. So really, we only need the moles. The volume really doesn't matter. Does that make sense? Anybody lost with that? Okay. It really doesn't matter how much you have. So I'm going to take my 0.06 and I'm going to subtract the amount of my base that was added, because it lowers the acid amount and increases the base amount. Does that make sense? So 0.013, and then I'm going to divide that by 0.05 plus 0.013. So I subtracted here and added here, so really, I don't know if that makes sense to everybody. Yay? Nay? This is just the strong. So if this was a strong acid that I added, if I wanted to increase the pH, then I would add it to the acid and subtract it to the base. Does that make sense?
So you're subtracting the base
From the acid, from the weak acid,
the weakest, right?
and adding that same value to the conjugate base.
And why is that?
So we are when we add a strong base or a strong acid to a buffer solution, then if we add a base, it increases, it changes the pH from going to more basic, right? And that makes sense in our mind, right? It's going to make it more basic. If we add a strong acid, it's going to make it more acidic. So that's why we subtract it from our acid, making it more basic. We add it to our base, making it more basic. Okay?
So what is a buffer solution? What is its purpose?
The purpose is to maintain the pH in a system.
So
And-
like with my
and-
hydroponic stuff, it's like when I add the pH up or the pH down.
It only goes a little bit. So
Right.
when we want to change the pH, it just changes a little bit. And I'll show you both cases. I'll show you a case where we change it, or just find the pH change without a buffer solution. Okay?
So sorry, we aren't necessarily trying to get to neutral. We're just, like, not trying to get to a neutral pH. We're just
Trying to change our pH.
within.
We're trying to change it a small amount.
Okay.
Because maybe our pH, maybe our system is acidic. Our body is acidic. It's like, get heartburn all the time. We want to change it just a little bit, right? We want to make it more basic. So all we do is just drink some. No, I'm just kidding. No.
Drink some bleach and you're good.
No. But we're just going to add. This is the chemical reaction part of it. Now we might add different things in our body, right, to make it more alkaline, or to make it more acidic if it's too alkaline. I don't know. Does that make sense?
So we are trying to get to.
We are trying to
neutral, but towards.
toward it, or just change it slightly,
Yeah. Okay.
whatever it was. So in this last example, we got a pH of 3.67, right?
Yeah.
And according to that, is that acidic or basic?
Acidic.
Acidic. Well, we need to make it more basic or more alkaline, right? So we're going to add a strong base to it, and it's not going to change it horribly. It's not going to bring it from 3.67 all the way to 12, for example, because then it'd be too much on the other side, right? So we want to change it just a little bit. And let's see what happens when we do this. So when we figure this out, we calculate it. It gives us our H plus. And you guys know how to do this mathematically, right? Parentheses first. We find that value, find this value, and then we multiply and divide, right? And we're going to get 1.34 times 10 to the negative 4. And then we find our pH. Our pH is now negative log of our 1.34 times 10 to the negative 4. And that's going to give us 3.87. Didn't go, it went up by 0.2. Didn't change it that much. So if I want to change it more, I'm going to add more base, right?
What was the original pH?
3.67 from our last problem. So it just raised it by 0.2. Not much at all.
Okay, sorry, I'm trying to selfishly make this applicable for me. In my
Uh-huh.
hydroponic examples, I'd like a storage tub with water and nutrients. Is that the buffer solution? And then,
So say that again.
so like hydroponics, I have a storage tub with water and nutrient solution.
Uh-huh.
In it. Is that my buffer solution? Because I'm trying to alter its pH?
Yes. Uh-huh.
Okay.
Yeah. All right, now. If I take my base, which is 0.013 in 1 liter, right? So if I take this and I find my my pH, it's going to be so this is my basically my OH concentration, right? Y'all with me? Because the 0.013 moles of NaOH to 1 liter of solution. So that's basically my OH concentration. So my POH is going to be negative log. And this is just a side note. We don't have to do this along with this problem. I'm just showing you what would happen if we just changed it without a buffer solution. So that's going to be 0.013. That's going to be a POH of 1.89. Therefore, my pH would be 12.11. So by adding a pH of 12.11 to water, it would change it by 5, right? But if I add it to my buffer solution, it only changes it by 0.2. You see the difference? What a buffer solution does? I'm not going to do any more than that. That's probably the hardest one I'm going to do. We can make it more complex, but we're not going to. Sound good? Yeah, Chad.
If we're making it, so in that last problem, if we're making it more basic, wouldn't we add 0.013 moles on top and on bottom?
No, because an acid adding a base, they don't go the same direction on the pH scale.
Oh, right.
So it lowers the pH of our acid and
Oh, right.
it raises the pH of our base,
Okay. That makes
or
sense.
concentration. Concentration, pH are directly related,
I see.
okay? Are we good? You want some good news? I probably won't even ask you that. I'll probably just have you use this formula to find out the pH. That's probably, in fact, that's all I'm going to ask you, okay? But I just wanted to show you kind of what it does, what a buffer solution does. Any questions? All right, we have the rest of today.
Can I use, write it down? Thank you.
We have the rest of today and one more time on Thursday to cover chapter 11. So that's all of chapter 10. We're done with acids and bases. Well, how do you feel? Was it too bad?
0.0.
It's just a little bit more dimensional analysis, few other conversions going from concentration to pH to POH, back to concentration of acid or whatever. And that's it. And then, of course, this equilibrium equation. But you're given all those formulas on the reference sheet. How do we feel?
What does that not say for these days?
Okay, good question. Let's talk about that before we move on. So I believe
It's Monday. Well, it's
Yeah.
listed as Monday currently.
it's currently Monday. Now, I don't know how many of you are going to take the final. But exam 5, we will be done on Thursday. That way, if anybody wants to do a big final review, we could do that on a week from today. Okay, and I don't know how many people are planning on doing the final, because again, I will drop your lowest exam score. But if you want to see how much you know, it'd be so cool, right? Look how much chemistry I know. Then,
How much final
what?
the STEM Center? There's a final review on Thursday.
This coming Thursday? Oh, thank you for that information. Final review this Thursday at the STEM Center, yeah.
So we did take the final, our final grade would be after we take exam 5, right?
Yes, so if you're happy with your grade, what your grade is after exam 5, and you're good with it, yeah, you can get a 0 on the final because that's the one I drop, right? And you will get a 0 on the final, but that's the one I'll drop. And let me tell you how I do grades. I don't change the grades in Canvas because that's the record. I take all your grades and put it in a spreadsheet and just, okay, I'm going to drop your lowest score here using a formula, and then I'll get your grade. Last semester, I emailed everybody's grade as I put it out there, because I don't know how long it takes you to get your grade. Do you guys? How long does it take? forever. Okay, so I will send out an email to everybody what their grade is after I've calculated it based off of the dropping the lowest and again, I'm on your side. I'm not gonna inflate your grades, definitely, but it generally the grades tend to just rise a snitch, right? But anyway, we good? All right. Is there a curve? You don't want a curve. So now, I do adjust the grades. I do. And it generally goes up a little bit. But I'm not going to curve it. If I curve it on the bell curve, there's definitely going to be people that fail. Definitely people that get an A. But most people are going to get in the middle. We're not going to do that, okay? But yes,
If we don't take the final,
then it will be dropped. Yep, it won't affect your score.
or
A what? Oh yes, I do round it up. If it's close, right? Like if you're like, oh, I'm like 0.5% away from an A, yeah, it's gonna round up. Because if you go half, anything 0.5 or greater, you round up, right? But if you're like a medium A, I'm not gonna worry about rounding it up because it's already an A, right? Or even a B. I'm not gonna. It's still a B if I round it up. So you know what I mean? Okay.
Some teachers don't do that. If it's even like just let's say
So C is.
like a 79 point something.
Do you know why? Do you know why they don't?
I don't know.
It's more effort. So maybe this is what you do. You get in good with your professors and maybe they will, maybe they won't still, I don't know. But again, I'm not going to inflate your grades, I promise. Okay. Ready for the last, any questions on acids and bases before we move on to chapter 11? We'll do part of it today and part of it, the rest of it on Thursday. And then review on Tuesday, following Tuesday. Yep. All right.
do